Hi, this is Penny, and welcome to this video on applications of quadratic functions. Let's review the main features of a quadratic function. The shape of a quadratic function is a parabola, and its vertex is either the maximum or minimum point on the graph. This graph also has one vertical axis of symmetry that runs through the vertex and parallel to the y-axis. In this image, the quadratic has one y-intercept and two x-intercepts, or zeros. But remember, a quadratic may have 0, 1, or 2 zeros. When two zeros do occur, they are always located at equal distances from the axis of symmetry. Therefore, if you know the location of the axis of symmetry and one zero, you can always find the other. There are three different forms of the quadratic function: vertex form, factored form, and general form. Each form has a use depending on the information we are given or what we want to know. Let's review the specifics of each form. The vertex form of a quadratic function is written as y equals a times x minus h squared plus k. This form is helpful when you are given information about the vertex and any other point on the graph. This form is often used when modeling problems involving projectiles, such as this water fountain, or in architecture, such as this window feature. The factored form of a quadratic function is written as y equals a times x minus r times x minus s. This form is used when you are given the zeros of a function and any other point on the graph. The factored form of the quadratic is especially helpful when asked to solve financial problems where a vendor wants to maximize their revenue. The third and final form of the quadratic function is the general form, which is written as y equals ax squared plus bx plus c. The general form is used when you are given the y-intercept, the parameters a, b, and c, or two of a, b, or c, and one other point on the graph. While it is possible to write a quadratic function in general form, given the y-intercept and two other points on the graph, this is beyond the scope of this course. Instead, we will only use the general form for problems where you've already been given a partial or complete quadratic function to work from, and you are being asked to find one or more key points on the graph. So which form of the quadratic function do I use to solve a problem? Well, this depends on the information you have been given in the question. For vertex form, you need the vertex and one other point. For factored form, you need the zeros and one other point. And for general form, you need two of a, b, and c and one other point on the graph. In this course, this form is rarely going to be used when modeling situations that involve quadratics. When this form is used, you will just be given the complete function to work from. And here's a hint. Make a sketch of the quadratic showing the key points you've been given to help you decide which form to use to model your problem. Here's an example. A diver completes an inward 3.5 somersault dive off a springboard platform. He starts 3 meters off the ground and reaches a maximum height of 4.1 meters. He returns to a height of 3 meters after 1 second. Let's watch Canadian diver Alexander Despatie perform the dive. Question A. After how many seconds does the diver reach his maximum height? So our first step will be to sketch the information. Here is what we know. The dive starts at a time of 0 seconds and a height of 3 meters. This can be written as an ordered pair of 0, 3. The maximum height of the dive is 4.1 meters, but we don't know the time when this happens. For now, the ordered pair is just written as a question mark, 4.1. This point is also the vertex of our graph. For now, we will draw a line to represent the maximum height since we do not know the full coordinate pair. At 1 second, the diver is at a height of 3 meters. The ordered pair is therefore 1, 3. We can now draw a rough sketch of the graph of the parabola for this problem. The time the diver reaches his maximum height is where the parabola intersects the blue line. Now we need to find the x-coordinate of the vertex. From our graph, we can see we are looking for the x-coordinate. This also corresponds to the axis of symmetry. We see we have two coordinates that have the same y value. This means they are equal distances from the axis of symmetry, and we can find its location by averaging the x values. So x average is equal to 0 plus 1 divided by 2, and 0 plus 1 is 1, and divided by 2, that gives us an x average of 0.5. Therefore, the axis of symmetry is located at x equals 0.5, and the vertex is 0.5 and 4.1. The diver therefore reaches a maximum height at 0.5 seconds. Question B. Determine a quadratic function for the height of the diver after t seconds. So our first step is to choose an appropriate quadratic function model. Let's review what information we have. We know the vertex h and k and 2 other points. In order to use the vertex form, we just need the vertex and 1 other point. Therefore, this seems to be the best choice for this given situation. So if our vertex, h and k, is 0.5 and 4.1, we also have a y-intercept, we'll label as x and y, and that's at point 0.3. We could use either point, but 0 and 3 is sort of the easier point of the 2 to use. Substitute these values into the vertex form of the quadratic function, and let's determine a. The first step to isolate a is to subtract 4.1 from both sides. 4.1 is canceled on the right side, and we are left with negative 1.1 on the left side. Let's clean up the contents of the brackets and square the result. 0 minus 0.5 is negative 0.5, and if we square this, we get 0.25. Now we will divide both sides of the equation by 0.25 to completely isolate a. This gives a result of a equaling negative 4.4. Therefore, our a value is equal to negative 4.4. Now that we have the a value, we can write the quadratic function in vertex form. Given a equals negative 4.4, h equals 0.5, and k equals 4.1, we can sub these values into our vertex form, y equals a, x minus h squared plus k. Therefore, the quadratic function is h is a function of time is equal to negative 4.4 times t minus 0.5 squared plus 4.1. Question C. At what time does the diver hit the water? Round your answer to the nearest tenth of a second. So here's what we know. When the diver hits the water, they are at a height of 0 meters. Let's mark this point on our graph. We can see we are looking at the right zero of our function. We have the y-coordinate, but need to find the x-coordinate for this point. It's easy to use a function to solve for a y value, but solving for an x value is a little trickier. You will learn an algebraic way to solve for this later on in this unit. For right now, we will use the calculator to answer this part of the question. Enter the quadratic function into y1. Set your windows to 0, 3, and 0.25 for x, and negative 1, 5, and 1 for y. Then graph your function. Now we can use the 0 function to find the coordinates of the point where the diver enters the water. To do this, enter second calc, number 2, 0. Move your cursor just left of the 0 and hit enter, then move it to the right side of the 0 and hit enter again. Press enter one last time and the 0 will appear at the bottom of the screen next to x equals. From the calculator, we see the 0 is located at approximately 1.465. Therefore, the diver hits the water at approximately 1.5 seconds. So when solving application questions involving quadratics, the best approach is to follow a few simple steps. Sketch and label key points from the question, choose the best form of a quadratic function to work with, create your function, and then use your function to answer the questions. Thanks for watching.